welcome to today's EOL seminar. On behalf of EOL, I'm pleased to introduce Dr. Nicholas Barron, no stranger to EOL. Dr. Barron received his bachelor's in physics with honors from Cleveland State University before pursuing his master's and doctorate in meteorology and atmospheric science from Penn State University. After obtaining his PhD, Nick joined NCAR's Earth Observing Laboratory as a postdoctoral fellow, working with Brad Klotz on the Airborne Phased Array Radar project. Nick was a key contributor to EXMIRAS, the explicit microphysics and radar simulator, for studying how dual-pol radar can estimate precipitation thermodynamics. During his time with EOL, he also developed the Osprey GUI for planning simulated APAR missions and conducted analyses using WRF simulations to assess the quality of simulations against available satellite observations. Currently, Nick serves as a senior radar scientist at Aeolus Labs, where he seeks to understand tropical cyclone dynamics by executing and evaluating ensembles of numerical weather prediction simulations, altering the thermodynamic parameterizations to understand tropical cyclone intensity sensitivities. He is also working to develop experimental design and logistics for upcoming field campaigns. Please join me in welcoming Dr. Barron for his seminar, A Variational Framework for Estimating Rain Microphysics from Dual-Pol Radar Observations. Welcome.
Thank you so much. I'm very excited to be here. I know some people know this, but I was a postdoc here for a year, and I never have actually been in Colorado. I worked entirely remotely, and so I was here at 3:30. Like, an hour ago, excuse me. I was like, am I in the right place? Maybe, who knows? But yeah, so I'm really excited to be here and see everyone in person in 3D instead of just a pixel or two on Google Meet. And yeah, I'm really excited to share what I did during my postdoc with everybody. Okay, so I wanted to approach the main problem that I was working on during my postdoc as what can APAR do, what systems can APAR observe that allow us to take the dual polarization capabilities of it and extract as much information about mesoscale convective systems as we can. And their mesoscale or MCSs are challenging to observe because sometimes they're extremely long-lived. Squall lines can last, on the order of days. Tropical cyclones, this is an animation of Hurricane Melissa, spends most of their time over water, and that's really hard to observe. But an aircraft enabled with radar can spend a long time observing these systems and going places where traditional platforms can't go. Now, like I said, airborne radar solves some of these problems. It allows us to take a peek into the kinematics and the precipitation for these systems. But it does not provide thermodynamic information about the storms. And that's really interesting for me. If we're talking about squall lines, cold pools are really important to them. If we're talking about tropical cyclones, pressure changes and temperature is all really important to understand. And here's a very funny picture or emission that I thought about how they deploy dropsondes in tropical cyclones. I believe this is from Hurricane Michael. And they take this flight path directed by these green lines here. And dropsondes allow us to, of course, observe temperature, dew point, pressure, things like that. And all the way over here, away from the storm, they drop about 16 of them. There's only around 30 every flight. Most of them are farther away from the storm. And then when they get closer to the storm, at the vertices of each turn, they drop some more. And so there's actually, in this mission, very, very few measurements of the inner core thermodynamics. Despite there being about 30 dropsondes, they're all just further away. And there are reasons for that, but it's frustrating for me as a mesoscale convective systems person. So what can we do with radar that allows us to take a peek into the thermodynamics? Radar does not give us thermodynamic information explicitly. It gives us information about hydrometeors, the size and shape. Most people here know that, but I want to make sure everybody follows along. If I say Z or reflectivity, it's essentially just a measurement of how much water is being scattered back from the radar. And ZDR, or differential reflectivity, it gives an indication of the shape or the size of the droplets. Because as water droplets get bigger, they become more and more hamburger shaped. And that gives you slightly different reflectivity that we can, slightly different reflectivity in the vertical and horizontal axes. So we can then take something that does actually give us some information on thermodynamics are microphysics and microphysics parameterizations. The hard part is trying to combine them all into one thing so we can take things like radar and say the information that microphysics will provide to us and use that to basically back out information about the thermodynamics. So that is how I wanted to structure my research project. There's information embedded in these, say, vertical profiles of reflectivity. So the microphysical fingerprints are there. All of these vertical columns are highly autocorrelated with each other. There's information that we can pull out. And things like evaporation, phase change, those show up in the radar measurements. So it's what we then want to try to do is take the warming and cooling effects from these different processes and just apply it to these columns of radar measurements. And from there, I wanted to be able to estimate evaporative cooling and squall lines. And this is a sort of a way to estimate the maintenance of the squall line. So one way that you can express this is the speed of the squall line. And if you take the relationship of a density current, the speed of that, and then you perform some differential equations and just you can actually rewrite it in terms of the cooling rate required to maintain that speed. And so it essentially just comes down to the buoyancy generation or the negative buoyancy generation caused by evaporation. It just needs to maintain a certain level of cooling. Okay, so there's essentially three parts to the problem here. One, we have to figure out a way to evolve a drop size distribution over time in any given environment. And this is just microphysics. We could take a Morrison model or SBM or something like that and go forward with there. So the next part is we need to calculate how a radar would see these observations. And this has also been done in different ways, like CRSIM or AOSPRI, which is built on CRSIM, allows you to just simulate radar measurements of drop size distributions or other types of distributions. And then we actually need high quality range height indicator observations of an interesting mesoscale convective system. This was somehow extremely challenging to find. So let's just start by checking off that box from the top. The microphysics problem, it's just a way to evolve the drop size distribution over time. So you can say over at the top, say at 2 kilometers altitude, the drop size distribution might look something like this. A generalized gamma distribution is often used for this. And then after the raindrops fall, the DSD at the bottom is going to be slightly different. Things like collision-coalescence, evaporation, there's size sorting, a bunch of processes going on that will slightly shift the DSD over time. And taking all of these rules into account, I built a simple binned microphysics simulator that allowed me to just explicitly program in these various drop size distributions and simulate them over time. It's available on my GitHub. I believe it's also linked in other places. I'm sorry, I don't know exactly where. I'll have to come back to that. So the next part is the radar simulator. And this is using a very similar method to what's been done before. It uses computational electromagnetics, T-matrix, to calculate things like the scattering table or different phase coefficients for how radar beams of different wavelengths would interact with the water droplets of various different sizes. And I solved these for a variety of wavelengths and then used parameterizations for the aspect ratio of water drops. But really, this is not, I think, the interesting part. This has been done before in many different applications, but it does allow us to, rebuilding it from scratch, one, allowed me to learn a few things, and two, it just allowed us to use the physics that's been used over the past 20 or 30 years, but just tune it directly for my application without trying to take something like CRSIM and plug it into this application that doesn't quite fit for it. So for example, we could solve a radar variable reflectivity using this equation here, or there's essentially just different ways of doing that for the various different radar variables. Excuse me. Now, in order to get an accurate profile of drop size distributions over time, you first need to have a good starting point. And so let's say if we take a radar observations at 2 kilometers, what drop size distribution should we fit to that and then simulate forward from there? Something that I find kind of funny about this is, say, let's just take 2 different radar variables, the reflectivity and differential reflectivity, so how much water and shape of the water. We can reconstruct these 2 values using a basically infinite number of different drop size distributions, ranging from this dark blue line, which is essentially just drizzle, very small droplets, all the way up to this green line here, which is heavy, fall on your head, hurt type of heavy rain. But all of these distributions add up to those 2 values for reflectivity and ZDR. And so you can see the problem here. The evolution of these different DSDs is going to be very different. And so what this what these plots show is the altitude is on the y-axis. So we're starting at 2 kilometers altitude, and then taking these same drop size distributions from here, going from the darkest colored ones or the drizzle type DSD to the lighter colored ones are the heavier drops. And we can say for 2 different environments, one being a very dry environment and one being much more humid, what happens when we evolve those DSDs forward? So in the driest case, pretty much all of the drop size distributions, just the reflectivity decreases over height, and that's just due to evaporation. But what happens when we go to the more tropical type environment, the reflectivity can either increase or decrease in respect to its altitude because of the nonlinear interactions between things like collision, coalescence, and evaporation. So when we're looking at the drizzle type distribution, the reflectivity increases by like 1.25 dBz. But then if we go all the way to the larger drop size distribution, it actually decreases, which is kind of funky. So this is just, there's a couple of interactions here, like I said, collision coalescence. It is essentially the larger, faster moving droplets moving through a medium full of smaller, slower moving droplets, collect them as they go down. Evaporation impacts smaller droplets more than it does the larger droplets. And so the combination of these 2 things shift these distributions around pretty substantially. And I think that this is best displayed when we look at the differential reflectivity and not just the reflectivity by itself. So If we then just perform the same analysis we did before, looking at the dry environment and the distribution that has a ton of very small droplets, what we end up is an increase in the differential reflectivity. What that means is all of the small drops just poof, disappear, evaporate. The only thing that are left are larger, bigger drops, and so that shows up more in the differential reflectivity. If we go to the bigger droplets, there's a decrease in the differential reflectivity, so there's a decrease in the average size of the droplets. What that means is just the evaporation, there's not a lot of small droplets, so the entire distribution is just shifted over a bit. And when we go down to the tropical profile, there's again the same sort of variation here. There's a very small signal. I don't want to spend a ton of time talking about it. If you want to know more, I can send you the paper. But if we say look at a difference kernel, so instead of looking at a vertical profile and how these values are changing, what this shows is how the drop size of a given size, the drops of a given size change between the top and the bottom. So all of the values that are above 0 indicate that drops of this size, the number of them increases by the time the drops hit the ground. And when they're below the line, they're decreasing. So if we look at the smallest, the drizzle type distribution in the driest environment, all of the drizzle drops just sort of disappear. They evaporate, just like we were saying earlier. This is essentially the same case for everything here. There's just a downward shift in the average drop size distribution. When you end up with large droplets, there's a decrease in the number of large droplets and an increase in the number of small droplets because the whole thing's just shifting over. And when we look in the more tropical environment, the collision-coalescence is more important than the evaporation. And so, say, look in the smallest drizzle-type drops, the smallest droplets are being consumed by the time they hit the ground. But instead of evaporating and adding to relative humidity, they're being consumed by larger droplets around them. And so they're just pushing over the medium to large size droplets are growing at the extent of small droplets. And then that's pretty much the case for all of the different drop sizes. Once we get to the far end of the spectrum, there's really not any small droplets to be absorbed by medium to large droplets. So the small amount of evaporation that actually happens can be seen right here. So this sort of emphasizes the problem. We need to have good estimates for drop size distributions because they're so different as we change altitude. And just getting that initial condition to run the assimilation is sort of what everybody's been doing in radar physics for a long time. And I'm not saying I solved it, but definitely not. But that's sort of the crux. And I thought these were really interesting figures to communicate that. So how does my methodology go about trying to solve this problem? Well, the first thing we need to do is look at an arbitrary observation, obtain information about the temperature and dew point, relative humidity, pressure, all of those things, just from a local sounding. Then what we need to do is run simulations that match that environment. And then vary the DSDs that we simulate over. And essentially from there, what we can do is build a lookup table of all of these different conditions and try to figure out which initial drop size distribution best matches the observations that are available. And so instead of looking at point-by-point DSD retrieval, it's looking at an entire column of reflectivity and trying to fit it to these profiles of the simulated drop size distribution evolution, the simulated rainfall that we have. And then once we go through that variational calculus, the one that is the best fit is the one we use to move forward. And once you have the simulations, then you can get things like rain rate and cooling and other things like that that are implied with the radar observation. So for an example, we can look at a case study from Precip, and specifically I'm going to look at S-POL, mostly because I think it's a really clever name. It's a C-band radar, and it's on the sea. Okay, I'm glad I got a chuckle, because I was on the plane practicing this, but nobody's going to think that's funny. There were atmospheric soundings released all the time during Precip, so we can just pick at a time when there is a good convective cell being observed with an RHI scan. And so you can see this is a relative, maybe not mature convective cell, but it's not decaying yet, and it's mostly homogeneous across the board. And the reflectivity is mostly in the 30 to 35 dBz range, and the differential reflectivity, it increases with decreasing altitude and going from around 1 to 1.25, 1.5, something like that, dB. So let's just take that information, build a CFAD out of it. So this is just a distribution with height, and then do the analysis we were talking about earlier. And I realized that the black does not show up very well on here, but essentially once we go through, we can fit all of these different curves to this line and figure out which one works best. And when we do that, I end up getting these values over here. Reflectivity of about 38 dBz at the top, ZDR, and the average droplet size of 0.6 dB and about 1 millimeter respectively. And we can just, this I should say is the horizontal reflectivity on the x-axis here, height along the y-axis. These lines are the same ones we were looking at earlier, but just trying to optimize for the fit that we have for this CFAD. This is the differential reflectivity, the same exact thing. It's a little bit harder because differential reflectivity doesn't vary as much, and we'll get back to why that's a bit of an issue. So throughout the years, I guess, there's been these shortcuts to retrieve the drop size distributions using a constrained gamma distribution. And so there's different shape parameters and size parameters in the gamma distribution there's a relationship between them that people have been able to find for various different environments. The Florida relation here is in this yellow dashed line. And I say Florida relation because they did it in Florida. So it's a mostly tropical type environment. They would run the disdrometer for a certain amount of time, record what that drop size distribution looked like at ground level, and then fit a gamma distribution to it. When you do that enough times, they build up all these scatter points and then fit a curve to that. There's another good case of this dashed red line, which is from Oklahoma. And so there's a tropical type relationship and more of a mid-latitude type relationship. And when I did the same thing with S-POL and using the analysis that we were just discussing here, the heat map over here overlaid on top of the Florida relation is actually a very, very good fit. And so this is at least encouraging that the methodology is bringing something in the realm of realistic. Like I said, overall, I think this is encouraging. Our heat map builds very, very closely to that Florida relationship. Now, let's actually get to a real-life example of applying the whole process and seeing what we can get out of it. So there's a squall line progressed from mainland China to Taiwan during the Timex campaign over in June 14, 2008. S-POL was used during the field campaign, and so we can use that data and try to move, see what we can do with that. You have no idea how long I looked to find RHI observations of squall lines that are publicly available. It's really, really challenging. So maybe we can do that more. Pretty please? Okay, so here's an example of one of the scans that I used to test this. We can take the RHI observations and then interpolate them to a grid of 50 meters by 50 meters, so horizontal by vertical. And then I just estimate the speed of the squall line just by looking at the average Doppler retrieval, Doppler velocity from the observation. There was a radio sonde released about an hour before these observations were taken, so great relevant information about the thermodynamics. And then we can just build our drop size distributions and run the microphysics simulation and try to back out information about that cooling rate to see if maybe it's close to what we should expect here. And so this is the results. And I'm going to take a second to explain what's going on here. So this is the RHI observation we saw from earlier. This is just re-gridded onto this 50 meter horizontal resolution by 50 meter vertical resolution. The top one is in distance, but it's just if you divide the distance by the speed of the squall line, that's why you see a time down here. And so this is essentially the same coordinate, but just so so you can understand like how big things are. Now, we perform the DSD estimation for every single horizontal grid point here. And then from there, that allows us to then move those drops forward in time. And so there is essentially, we just have this Eulerian point in space, and we allow the squall line to pass over it. And then we just update what the drop size distribution should be at each point in time, and then just keep the simulation moving forward. And it feeds back into the environment, so when drops evaporate, they increase the relative humidity and change the temperature, and things like that. So the result is then the simulated reflectivity using the DSD estimation. And overall, I think that this matches fairly well. And there's a few different regions that I want to point out here. There's this first part here, which looks like maybe the convective leading edge of a squall line. It's not quite developed yet. You can see precipitation aloft, but it hasn't fallen down all the way. There's no dynamics being considered in the microphysics model, so it would never be able to resolve that effect properly. And that's okay. But let's move a little bit further to this deep precipitating, or this heavy precipitating core. And the results from the DSD assimilation overall seem fairly close. We end up seeing about these 3 different regions. There's a heavy precipitating core right here that's being resolved fairly well. And this gradient leading up to it is also fairly well preserved. And then we can move to this second area where there is another weaker precipitating core that's also being resolved fairly well. Then beyond, and I think that this is very interesting, you can see the effects of the different sedimentation rates of different sizes of precipitation showing up, so that in spite of the fact that there is a weaker vertical velocity aloft, the way that everything coalesces and combines, we end up creating this upward sloping structure fairly well. And there is some more precipitation below it that isn't being captured with the observations, but overall, I think this is pretty good. If we do the same thing, but just plotting the differential reflectivity instead, the results are not as great. This is likely because the signal of the differential reflectivity is substantially, the ratio of the signal to the error in the differential reflectivity is a lot lower, or a lot higher, excuse me, in this case. So it's harder for the variational methods to actually converge onto a great solution for differential reflectivity, unlike we can see in the reflectivity plots. But the errors are not terrible. We end up getting about 0.5 to 0.3 dB across the board. We still are capturing this central cell reasonably well. We're not capturing this cell. Again, we wouldn't be able to anyway because of the different dynamics going on. And everything else is, it's okay. But because we have a full simulation of the microphysics, we can then directly extract things like cooling rate, things like rain rate, all of these different values, or things like the relative humidity expected, the change there. And so when I do that, take out the cooling rate from the model simulation, what I end up getting is this rate of about 2 degrees Kelvin per hour. So as the rain's falling, it evaporates, cools down, and then that helps propagate the cell even further. And there is a way, like I said earlier, you can rearrange that speed of the density current equation in terms of the cooling rate. And you end up getting this curve that looks like this. This is environmental shear, and in this case, speed of squalling could be the same thing. But when I look at the cooling rate of about 2 degrees Kelvin per hour, I end up getting the speed of that squall line should be about 13 meters per second. And the system's average Doppler is 13.02 meters per second. And I do believe that that very close number is probably a bit coincidental, because when I look at other examples, I generally get about 1 to 2.5 meters per second of error. But, you know, this is a great example, so why not show it, right? Either way, everything points to the results from this methodology seem somewhat realistic. We can also perform an additional step in validation, looking at the specific differential phase. And this is somewhat related to the size of droplets that are being scattered in the volume. It's related to differential reflectivity, but they're not exactly the same thing. We also don't include the specific differential phase in the cost function for obtaining the drop size distribution in the first place. And so this seems like at least an additional data point on that validation curve. And just like before, I have the RHI observations regridded onto the simulation mesh. The specific differential phase is over here, and the results from the simulation are down here. Overall, also seems very close. We end up getting these same location, around the same magnitude of the specific differential phase. This first peak is fairly well resolved, and the second one is also being resolved fairly well. So I hope that that's a good place to have the validation. At least things seem realistic. So what can we do with this? Airborne Dual-Pol weather radar, they're not operational right now. But if they were, we could perform similar studies flying into tropical cyclones. We could perform similar studies flying along squall lines like this example here. This is a simulation that, a CM1 simulation of a squall line, and we ran the radar observations through Aeolus. And so this was hopefully about as close as we can get to simulating what APAR would do when it's ready. When we do the same analysis as before, then these are, of course, going to be a bit messier because they're simulations, but we're still getting reasonably good results. The structures are being resolved, so the drop size distributions should be roughly correct as we're going forward here. I don't want to spend a ton of time going over these because they're very similar to the plots we saw earlier. But things like cooling rate, changes in relative humidity, we can resolve all of those things through here. So in places where long-lived squall lines and radar observations, ground-based radar observations can't keep up with it, we might be able to use a methodology like this to capture maintenance and how the actual like interactions that are going on between the precipitation and that feedback mechanism. Same thing with tropocyclones or atmospheric rivers and all of these different things. We could observe these and try to look at how the different thermodynamics are at play. So, in conclusion, vertical columns of dual-pol radar observations, they have these microphysical fingerprints that we can pull out and learn something from. And using the variational framework that I was discussing earlier, we assimilate the observations and to obtain drop size distributions and cooling rates and other variables from there. It does seem to reproduce the structure of the radar observables, and like I said, gives us this interesting point of data from the retrievals. Something like this might be able to allow us to bridge a gap between more mesoscale data assimilation and convective scale data assimilation. However, we need to design our observation strategy to match the needs of a convective DA system. It requires observations of these small scale features that are just really, really challenging to get to. And so I'm going to spend a moment here to talk about what I'm doing right now at Aeolus Labs. Convective scale data assimilation is one of our goals. We're currently trying to solve this problem by building a GPU native differential LES model. This has about 10 times speed upgrade from WRF at a similar resolutions. Obviously, WRF is not really made for 1 kilometer resolution. You can run it at that, but for 1 kilometer resolution, things like LES and something like this is, I think the best way to go about that. But we're also working on developing new DA pipelines that are hooked into this GPU-ready model. And we're trying to figure out ways that we can assimilate specifically convective scale information and not just, there is a cloud in this 27 kilometer bubble over here. How can we do that at a smaller scale on the 100 to 500 meter resolution scale? And we're trying to engineer new observation platforms so we can study tropical cyclones consistently. And all of this is trying to bring in weather resilience in tropical environments. If you're interested in collaborating, let me know. We can talk now or send me an email later. And that's everything I have. Thank you so much for listening.
Great, thanks for that, Nick. While people are coming up with their individual questions, we have a clarification question online from Chris. Chris says, you showed a comparison between a theoretical propagation speed and an average Doppler velocity. Was that a Doppler velocity at the steering level? Did this match the speed of propagation according to reflectivity?
What was the last part of the sentence?
Did this match the speed of propagation according to reflectivity?
Yes. So admittedly, the approach that I took was very naive. It is weighted by the reflectivity. So it should be the speed of those precipitating cells. There are better ways to do that, but this is a fairly quick and dirty test. I should go back and properly calculate these before we before we go through the publication process. Yes. Thank you for the question.
Cool. Thanks for that. Chris, let us know if that didn't answer your question. Are there questions in the room?
Thanks for the nice presentation. I'm really fascinated because I'm trying to figure something out very similar, but on a smaller scale in terms of fog, and looking at droplet size distribution and cooling and so on. So this is really inspiring. My question is here, like there's also changes in your advection, in your air mass that is advecting together with your hydrometeors. Yeah. And you're basically focusing on the cooling and heating to either droplet formation or evaporation. What is your feeling about the role of also dry air advecting or moisture advecting with the mean flow?
That is a great question. Those things are really important, and we see, look at something like a squall line, there's a rear inflow that's bringing in different air than what we'd be experiencing at the beginning of the, I guess, the convective leading edge of the squall line. Sort of what I'm assuming is there's no mixing going on. That's not true at all. But in order to resolve that, I'd have to run a full simulation, and then we sort of get to this chicken and egg problem of how do we build how do we get to how do we solve the variational calculus for that optimization problem with all of these chaotic implements in there, that field of solutions explodes. I really wish I had a good solution for that, but I don't. And I would love to chat more about it, because that's what I'm trying to solve every day at work right now.
Great talk, really appreciate it. As a data person, I feel like I need to ask why it was so difficult to find the RHIs of the squall line. I assume it's for both two reasons, in that radars often aren't observing the squall line in the exact way that you want them to, or in the case of what you needed for. And then also it's just difficult to understand where to find those kinds of data sets. So couldn't you elaborate on that a little more?
Yes, it is. It's hard to, oftentimes when you're, say, downloading something from EOL's like archive, it doesn't say what is inside each of those files. So let's say we download the hour before I showed in the squall line example. Actually, no, let's do the hour after. There aren't any RHI observations in that following hour. It was all surveillance mode. And so we actually have to go through manually every single one of them. And that's really, really time consuming. And on top of that, having dual-pol RHI observations limits our pool of platforms even further. And so there's like easy ones like C-POL and S-POL. There are other research grade radar that do have these nice observations, but they're often not publicly available, and that really slows down the speed of development when we're waiting on PIs that worked on this project 20 years ago and have to find the tape that holds that part.
Yeah, that sounds almost impossible in my eyes. But yeah, so you're trying to say that adding the scan strategy as some metadata piece to the files would be helpful, or at least within the data set somehow.
Yeah, that probably would be helpful, but I don't know how to, it's also a volume problem. If you showed every single RHI scan when it has a very heavily used RHI, then there are examples when there's like pictures of the radar scans available. They can just like click on the time, but it's hard to get every single one of them. And then it's like at which angle relative to the radar. Yeah, it's really challenging to get to finding the right observations for something like this.
Yeah. Thank you. Appreciate it.
Thank you.
Thank you. Thank you for your talk. I had a quick question about your slide where you did the comparison between the Eulerian point and the model. Yes, that one. One, I noticed that I think the model ends at about 2,100 or meters versus the actual height. Is that just what, or why didn't you extend the model up higher? Or was that not worthwhile?
I was just using 2,000 meters as a reference point across the board. We can go higher. It has to be below the LCL, or not the LCL, the melting layer. Otherwise, we have things that aren't being resolved in the microphysics happening. But also, we want something. Ideally, it would be looking at something beneath the cloud layer entirely. So it's just what's happening is just precipitation. 2,000 meters is not below the cloud layer, but it seemed like a happy medium. When I went too high, we ended up, the optimization wouldn't work at all. When I went too low, there just wasn't enough information for the fit. So I had to go a little bit higher. I could have, 2,500 meters is fine. Once we start to get above that, things get a little sticky.
Thanks. And then on the difference at the ground between the radar and the model, is that just what the radar is able to see, or is that a difference in the model itself?
The difference in the ground,
Yeah, especially towards the right,
this,
all of that, where the ground starts fading away and you still have model data.
yeah. What I believe is going on is this is mostly stratiform precipitation, so really just drizzle. I think we might have an updraft that's just holding things up there. And so it's the radar can see it, but it's not quite hitting the ground. And then we can't resolve dynamics like that with the way that this model is set up.
Great, thanks.
Thank you.
Well, I'm on the author list, so I'm not supposed to ask questions, but you brought up a few points that I just hope you can elaborate on that. One point is that you said observation strategy, something like observational strategy need to be tailored for DA purposes, something like that. That's a trend in the observing community. And TIMREX 2008 was probably the first time I'm aware of that a DA component had a big say on how we scan the radar. And I see more and more common that we're doing that type of scan. So the question for you is, before we have phased array radar that can do everything you want, how do you recommend we scan a ground-based radar in order to do this type of work? So that's my first question. The second question is that, the previous two questions, two staff asked the first part of my second question, which is you're assuming a two-dimensional problem, and in reality it's a four-dimensional problem. So how do you see the path that this work can be linked toward a more sophisticated modeling like John Kelm is working on, more than a four-dimensional DA?
Yeah, okay. So the first question, how do we scan the environment? Without things like phased array, there was a demonstration that Pavlos Kallias had in one of our meetings I thought was really cool. And I don't think this is a novel idea, but he had a cool animation of it. And basically just a surveillance scan, and then once you hit a certain threshold in the reflectivity, he just did a vertical scan there, and then moved around and kept that going, basically. And the idea was that we can build essentially like the velocity structure of our system and then try to tailor to where it's going to be so we can update the scan so we're not spinning around in azimuths that just doesn't matter. But then we're also high sampling rate with RHI scans of the convective parts, or we can, we could scan whatever you want to do using that. Without something like phased array, I feel like that's a pretty good solution. But that's also you're sacrificing. There's always trade-offs with radar, and in that case, you're just focusing on one system, or you're splitting time. And so I don't know how to do that without phased array radar. And something that we're working on right now at Aeolus Labs is with the differentiable structure of the model, we're trying to use gradients to actually inform where you can scan radar. So there's a high uncertainty in that area. Let's shift the beam, shoot over there, and then we can adapt to where all of these, we need to have certainty in the DA scheme. I feel like something that is probably the future. I don't know if that's like Star Trek future or like something that we'll achieve in our lifetime or not, but I think that's like the best place that we can do with radar as a technology. The second question is, it's a 4D problem. So things like 4D variational data assimilation, that's
Maybe that's too far down the road. But
maybe.
What I'm asking is that, I mean, there's a value of this approach. You can generate a drop size distribution that's close to balance between the model and observation. So you have one, in this example, you may have a several RHI scan that you can apply. Then how do you see the link between your work here to the next step? That's forget about 40 DA. That may be too far. It's okay. Any thoughts on how you expand this work into maybe a 3-dimensional rather than a 2-dimensional?
Yeah, the way that I set it up with just a point in space and then letting the squall line pass over it, I think that's more of it's conceptually very, very simple. We can still go on a point-by-point basis, or we can even go with like a clustered approach to say all of these points in space with like a moving, essentially a moving average, a convolution in space, and then taking those columns and then performing this system, and then going forward in time, or forward all over the place, and then taking a step forward in time, and then, iterating like that. That should work. It's obviously there's going to be some issues with advection and dynamics that we just aren't resolved in the current setup, but there's nothing inherently limiting with that approach for something like this. Obviously, this is a pretty naive way of solving the problem. I think it's just a jumping off point.
So let's thank Nick one more time. He will be in town through tomorrow, and then he'll be back for the radar workshop if you want further discussions.